Okay, so this is the first session on kinetic physics, which will be followed by Sasha's presentation later on in the morning, and then our practice session in the afternoon. I have one request for all of you, which is be brave and ask questions. Okay, every question is welcome, and it's your duty at this school to learn, so just try to make the most out of it and ask all the questions that pass through your head. Okay? And actually, yep, that's exactly what I wanted to say. I will be using this to poke you so that you actually ask questions. It's extendable. Okay, so this is the outline. I will try to leave it here on the board. We will talk about plasmas, what we mean by plasmas, then introduce the Vlasov equation, which is the fundamental equation to describe plasmas, and the Vlasov-Maxwell system. This system of equations is what's described in the so-called particle-in-cell simulations. I will be describing how the distribution function, which I will be defining, can be represented by a collection of particles that are followed in a Lagrangian way, and then the basics of the particle in cell, the peak loop. And then there will be a few applications if we have time afterwards. Okay, so what is a plasma? A plasma is a gas of ionized particles. And it's convenient to define some time and length scales for plasmas. The fundamental time scale is the inverse plasma frequency, where the plasma frequency is defined 4 pi. Density is square divided by the mass to the 1/2. This is the characteristic frequency of oscillations. If you have a box with electrons and protons, we are displacing the electrons one way. The electrons will come back and start oscillating back and forth with this characteristic frequency. With the plasma frequency, you can construct a length. It is the so-called Debye length, which is the thermal velocity of your plasma divided by the plasma frequency. And the Debye length gives you the characteristic scale over which charges are screened. So if you place a positive charge in a plasma, this charge will attract negative charges closer in and push positive charges further out. And the typical length scale over which the effect of the positive charge that you introduced is screened, exponentially screened, is the Debye length. The Debye length is used also to define how coupled the plasmas are. So it's useful to compare the Debye length with the characteristic interparticle separation, which is just the density to the -1/3 power. This is giving you a characteristic distance separation of particles just based on the density. And for most astrophysical systems, the product, which I'm going to call number of particles in the Debye sphere, which is the number density of particle multiplied by the Debye length cubed. This is a number of particles. It's much, much larger than unity in typical astrophysical plasmas. So within that Debye sphere, you have a lot of particles. In addition to the Debye length, you can define something that is called skin depth, which is similar, but speed of light instead of the thermal velocity. This is the characteristic penetration depth of an electromagnetic wave into a conductor. So the electromagnetic wave will be damped in space, exponentially suppressed once it tries to enter a conductor on a characteristic scale that is this much. And then you have, in principle, other time scales and length scales. If you're in the presence of a magnetized plasma, you can have the Larmor frequency, let's call it omega L, and the Larmor radius are L, if you have a magnetic field. Where are these wavelengths, where are these lengths and timescales as compared to fluid scales, which was the subject of the first couple of days? Okay, let me write it here. So the hierarchy between the different plasma scales, I will not be discussing it too much, but typically the electron Debye length is the smallest, which is smaller than the electron skin depth of the electrons, and the electron Larmor radius. And of course, these are very much smaller than the ion corresponding quantities, the Debye length of the ions, the Larmor radius of the ions, and the skin depth of the ions. And then the ions are much, 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 much smaller than fluid scales. So we're really looking at a, question. Excellent. Excellent. We'll talk about that. The mean free path depends on an extra degree of freedom, which is the collision frequency. And it distinguishes whether a plasma can be called a collisional plasma or a collisionless plasma. Now, for most of the astrophysical situations that we care about, the mean free path is much larger than all of the plasma scales. And then, depending on the system, it could be much, much larger even than the fluid scales, or comparable to the fluid scales. This entirely depends on the physical conditions in the system, like density and temperature. So what we will be focusing on today is primarily plasmas that are, that's actually an excellent segue from what I just discussed, preferentially plasma that are so-called collisionless, in which the mean free path is much larger than the plasma scales, and it's also much larger than the typical fluid scales. And there are a number of sources in astrophysics that are actually collisionless plasmas. So this is what I'm showing there. And these are the sources that you should keep in mind when you want to model things with kinetic tools like the particle in cell method. Relativistic jets from active galactic nuclei or from stellar mass black holes. Pulsar wind nebulae are bubbles of synchrotron emitting plasma around pulsars, pulsar magnetospheres as well. Gamma ray bursts as the recent neutron star binary merger event. Galaxy clusters are also very weakly collisional. Even though they are gigantic, these are megaparsec scale structures, the mean free path is comparable to the size of the system. So even galaxy clusters, despite how big they are, they're just barely collisional. And fast radio bursts, which still we don't know what they are, I will not say much about them, other than they are fast, they are emitting in the radio, and they are bursting. And this you have seen already from the presentation that Charles gave, the image of the black hole at the center of M87. So for all of the systems, we require a collisionless description because the mean free path is much larger than plasma scales and much larger than the system size, or comparable to the system size. So what is the preferred way of describing collisionless plasmas? And I want to introduce a couple of definitions first, and then we'll go back to the board. So this is something that you should be already familiar with from the fluid perspective. One can define a view that is Lagrangian, meaning that you're following the motion of a given fluid element, for example, as it moves through space and time. You're just sitting on top of the fluid element. This should be contrasted with a Eulerian approach or a Eulerian view, in which you're just sitting in a given position in space and you're seeing the fluid element passing by. Okay? So these are just two different approaches, two different ways of looking at the same physical process, which could be hydrodynamics or magnetohydrodynamics, but it applies as well to the description of plasmas. So let me just put it there. Let's go to this one. So the Lagrangian versus Eulerian perspective is useful at the moment of describing plasmas thanks to the fundamental equation that is capturing their behavior, which is the Vlasov equation, which I'm going to introduce now. And for that, it's useful to define the so-called phase space density. Which we call F. And it's a function of coordinates, momenta, and time. So it's a 6-dimensional function. We also call it distribution function, which is evolved in time. Okay, and it describes how many particles you have in a given volume of physical space and a given volume of momentum space. Okay, so that's a fundamental concept. Yes, Magda. So as you will see in just like a couple of minutes, you can always get back to the fluid equation starting from plasma fundamental equations, but in some systems, the fluid approximation is correct, and it's very accurate. These are definitely systems in which the collision frequency is very high. Then it doesn't make sense, or it's not very useful to describe the system as a collection of individual particles, as we will be doing, but you should describe it as just like a fluid element, because what you place there, due to collisions, it's stuck there, okay? You don't have particles flying away. But in systems in which the collision rate is very low, the chances for collision are very low, then you can still describe it with the fluid equations, in principle, but you're making kind of a sort of like a brave and possibly incorrect approximation. This is the case for all of the systems that I described before. In fact, we do describe with general relativistic MHD the accretion flow at the center of our galaxy, knowing that this is a collision-less accretion flow. So we should not really be describing it with MHD because it's implicitly assuming a fluid-like behavior and so efficient collisions, but in actuality, in practice, it's not a collisional system. Now, this is entering into a little bit more complications because, okay, what are you actually defining as collisions? It's only binary processes, or there is like some effective collision that the plasma can still have, and make the approximation of MHD still acceptable, even in a formally collisionless system. Yes?
For your distribution function, does it have to have some kind of like general properties, or it can?
It should be positive, right? You're just counting the number of particles. The integral should be finite, because the integral should be the total number of particles that you have. I would say that's it. You should really be thinking it as the equivalent of a mass density. The mass density is just counting how many particles you have in a given position in space. This one is counting how many particles you have in a given position of physical space and momentum space. So how many particles you have within a given location of physical space with a given momentum or velocity. Okay, so Vlasov equation. Vlasov equation says that the Lagrangian derivative of the distribution function following the trajectories of the particles of the characteristics in phase space is equal to, when you don't know what the answer is, most likely it's 0. Okay, so this is 0. And this is a statement about the fact that you have no collision. So this 0 is appropriate for a collisionless system. And in fact, this equation, in addition to being called Vlasov equation, is also called collisionless Boltzmann equation. The Boltzmann equation has a collision term on the right-hand side. The Vlasov equation, or collisionless Boltzmann equation, has a 0 here. This is equivalent to saying that the phase space density is conserved along characteristic curves. It's also another manifestation of Liouville's theorem. Okay. No, the magnetic field is right there. Yeah. The only thing that you need to assume is that there are no particle creation processes or destruction processes, and you have no collisions. Think about it, if this is making it easier. Think about it in one-dimensional coordinate in space and one-dimensional coordinate in momentum space. And you have your distribution function here, which says how many particles you have, okay? And this has some momentum velocity, some coordinate, so it will be moving in general in this space, but it will be moving in a continuous way. And particles will not be created nor destroyed. This is where this 0 is coming from. It's different if you have collisions, right? Collisions are processes that will be able to place a particle that is sitting here and switch its direction of the momentum instantaneously. So the particle that was here will soon after appear here. This is not a continuous process. This is not something that you can follow along the characteristics, okay? And this process will violate the 0 here. But all of the physics of magnetic fields, external gravity, they're all in there, okay? They're not violating the 0 that you have on the right-hand side here. So if you were to think about systems in which this is applicable, okay, so we have justified this when we have introduced this for plasmas. Not the only system that is a collisionless system. How many other collisionless systems can you think about other than gases of charged particles? At least one. Dark matter. It's described by the Vlasov equation. Something else. Stars in a galaxy, they are virtually collisionless. The chances of two stars colliding is very low. The Vlasov equation is still a very good description for the system. Of course, the ingredients that get into the evolution here, coming back to what Pascal was asking, are going to be different. In that case, magnetic fields are completely unimportant, and gravity will be the one playing the role here for stars or for dark matter. But the conservation of the phase space is still valid for any collisionless system. Yes?
Would you call Coulomb interaction as collision?
Yes. Yes.
But the characteristic time is small. So is there some? The change of the momentum there is not instantaneous, but rather has a small, very small characteristic time.
Yeah. So
the 0 there, how to quantify whether it's a collision or not a collision.
it's a good question. I would suggest to postpone because it's a deep one. Let's postpone it to the coffee break. I would say the small time scale is virtually instantaneous for these processes, but exactly the conditions under which you can actually write 0 here need to be worked out very carefully.
One quick point would be that if you introduce a distribution function, which is a function of coordinates of each particles and momenta of all the particles, then the 0 still applies. But it's not a 6D function, but 6D times the number of particles function. So when you reduce that function to one particle distribution function, you get that collision check. And that's how you can formally derive the applicability of this equation. That's what's called the Klimatowicz equation. And then there is a reduction scheme with 5 names, like Bogolubov, Green, and Kirchhoff.
So you have another umbrella on top of this, which is for each single particle. And then once you're describing it in a 6-dimensional space, then you have to account for the interactions between the particles. And that's the point in which you are saying if the collisions are negligible. Okay, so the only other point that I wanted to make, and then I'm going back to the slides, is that from this equation, if you're writing it from the Lagrangian perspective to the Eulerian perspective, this becomes the derivative as a function of time plus dx dt df over dx plus dp dt df over dp equal to 0. This is equivalent. And from this, you can actually take moments and get back your fluid equations. So for example, if you just integrate in d3p that equation, you get out the mass density equation for fluids. If you integrate in p d3p, or v if you have a non-relativistic plasma, then you get out the momentum density equation. So as such, you can reconstruct the hydro equations based on this fundamental kinetic physics if you're taking just moments of your distribution functions in velocity space or momentum space. Okay, so for this specific case, oh wow, I will never be able to get that back. For the specific cases of gases of ionized charged particles that are primarily controlling by electric and magnetic fields, assuming there is no gravity, is an assumption, then in the Vlasov equation that is sitting right there, we can write the dx dt as v and dp dt as charge, and then the usual v over c cross b. This is the cross product, okay? Okay, so now we have all of the pieces. This is, of course, defined as P divided by the Lorentz factor times the mass. We have all the pieces for what's called the Vlasov-Maxwell system, which is on the slides right there. So you have the Vlasov equation on top. Here is for the specific case of a non-relativistic plasma, so I am phrasing it in terms of a velocity as a variable, but you should actually imagine it to be the momentum. And then you're coupling it with Maxwell's equations. Div B is included, div B is still 0, and the divergence of the electric field is 4 pi the charge density, but now we can construct the charge density as a momentum over, as a moment of the distribution function. This is just how many particles you have. You multiply by the charge of that particle species. You sum over the different particle species, you get the charge density. Same thing for the current density. The current density is nothing more than the first moment of the distribution function. This is giving you the mean velocity. And then with the charge density, you're all set for finding the electric current density. So this system is, of course, coupled. You're evolving the distribution function depending on electric and magnetic fields. The electric and the magnetic fields are provided by the charges themselves that follow and are shaped by the distribution function through these Maxwell's equations in which the distribution function appears to provide the charge density and the current density. Okay, so now the question is, how are we solving this system? And there are essentially two approaches. One is the so-called continuum approach, which relies on discretizing your distribution function in the 6-dimensional phase space. Okay, already this should be quite scary. This is very computationally expensive. You need to solve a function of 6 dimensions evolved in time. And there are a few more things that are not making it very attractive. How do you determine the boundaries of the grid in momentum space? How do you know that your distribution function will only get to a velocity of maximum velocity? You can set it by hand at the beginning if you want to have the same grid, or you need to regrid at later times if you find that all of your particles are accumulating at the fastest possible velocities that you have prescribed beforehand. And also, there is nothing in the evolution equation in principle that will preserve that distribution function should stay positive as it should. The advantage is that this method is actually very good for capturing weak effects. If you have a very low particle density or a very low occupation number of the distribution function in a given cell in phase space, you're still capable of capturing that, whereas if you have particle in cell methods, you might just say, I have no particles there, and I will set it to 0. So you will not be able to capture these subtle effects. The alternative, which is what we will be spending this morning most of the time on, is to sample the phase space with particles. So instead of having a continuum distribution function, you're just localizing particles there, and you're sampling your shape of the distribution function with a series of particles, which are Lagrangian tracers. So you're following them along characteristic curves. This is what the particle in cell codes do. You have particles that you're following in a Lagrangian way, in a continuous way, in phase space, and you're taking moments of the distribution function, most importantly the electric current density, in some codes also the charge density, and these moments are computed on a Eulerian grid. On the same grid you solve for Maxwell's equations. So this is the Lagrangian versus Eulerian approach. The particles are Lagrangian. You're following them continuously as they move through the grid. The information about the electric currents, the electric fields, and the magnetic fields are only at grid points. This is, in a nutshell, the particle in cell method. You have particles, you might think about an alternative approach. Which is just compute the forces, at least for an electrostatic code, in between every pair of particles. This is not very convenient. First of all, it's extremely expensive. You can do sort of like a tree model that will make it less expensive, but in the most naive implementation, it's an n-squared process, because every particle is interacting with all of the other particles. The Coulomb forces are long range. And also, forces are instantaneous, because you're taking into account the fact that one particle can affect another particle even before the light has had time to propagate from one side to the other. And also, again, in a naive implementation, you are taking into account also forces in between particles that are very close, whereas in reality, what we have seen before for a collisionless plasma is that the Debye length should be the minimum length over which you're feeling the presence of a particle. The electric fields beyond that length should be effectively screened. And instead, this method is not really ensuring that from a fundamental point of view. The particle mesh technique that I've just described, in which the particles are Lagrangian in a grid that is Eulerian, has an advantage over that, because the process is actually of order n, right? You will go through the various stages of the particle in cell loop afterwards. The point is that every calculation at every time step is just linear in the number of particles and linear in the number of cells. So you have a tremendous computational advantage. And since the electromagnetic waves are propagating on the grid, you're automatically including the finite light propagation time on the grid. Question? It is, effectively it is, yeah. Yes, exactly, that's what I said. In the naive implementation, you can have a smoothing length on the Debye scale. You can have like a tree, so that you don't account for very far away particles in an n-square process. Yes, all of this, yes. We'll get there. So, yeah, you have no restriction on the species, okay? The restriction that you have is that for, in practice, every particle that I'm going to talk about for the particle in cell loop is not really an individual particle like an electron, but you should think about it as a collection of electrons that are all clustered together, like a mega electron or a mega proton. They all have the same charge, they all have the same mass. So this mega particle that we call macroparticle has the same charge to mass ratio as a single electron or a single proton, depending on the species that you care about. So in the Lorentz force is moving in exactly the same way. The charge over mass is still the same. But still, it does represent a large number of realistic electrons. And this is increasing this downsampling of the actual particle distribution, because we we need to downsample because we cannot have as many particles as in a real system is causing noise, for example, shot noise. The fact that the particle distribution function is not captured at a high enough accuracy. Okay, so yes, you can have as many species as you want, but every particle is actually a cluster of particles of the same type. Okay, so let me go back to the board. I want to introduce now how the particle in cell method is dealing with the distribution function. Oh. Yes.
Maybe in the future, like maybe 100 years from now, when computational biology people will solve less of visions.
Oh, the continuum method.
Yeah.
Yeah, actually, they're becoming quite competitive. I would say they're much more established in the non-relativistic business than in the relativistic business. And at this moment, the real advantage is on limited dimensionality simulations. So 1D in space and 3D in velocity space or momentum space, it's definitely doable. Multidimensional in momentum space and coordinate space, it's still not computationally. But in 100 years, oh, definitely, yes. I will not be here anyway, most likely. Okay, so PIC method integrates the Vlasov equation along trajectories of macro particles. Each one is a collection of many real particles. So what effectively it does is to take the distribution function and model it as a sum over individual particles. Total number of particles, the sum is over the particles. This is the particle weight or the mass. And then you have a particle shape around the particle location, xi of t. And the particle has a specific momentum, so this is a delta function. Okay, so this is Dirac delta. And it's saying the particle has that specific momentum. And the shape is giving the sort of like footprint of the particle. You can take this as actually a delta function as well. You can say the particle is exactly at one location, but it's actually not convenient for reasons that we'll be describing later. It's called shape. And there is no single choice for what that shape should be. The properties that we would like to have is that it's positive, that it's of compact support, so it's 0 beyond a given distance away from the particle. You don't want the particle effect to extend to infinity. It is normalized to unity, and it's symmetric. So S of x minus y is equal of x, S of y minus x. But aside from that, you have absolute freedom to choose whatever you want. So in this spirit, the current density, for example, and the charge density is very similar, can be written as the sum over the particle charge, particle weight, particle velocity, which is related to the momentum, of course, and then the shape. Okay, you just plug in this definition in this is the definition of the distribution function into what the electric current density is, which is the first moment of the distribution function, and you get exactly that expression out. I will come back to the shape function in a little bit. Let me just use the board a little more. I think this is what Sasha is going to illustrate afterwards. But from that choice of the let me just anticipate it. From that choice of the distribution function, you can obtain the equations that your particles should be following. So you take that f that I wrote up there, the integral of x f in d3x, and then integrated in d3p, is giving for that specific expression dxi dt is equal to vi. Okay, so the Vlasov equation, sorry, not this, got it wrong. You should have Vlasov here. So take Vlasov equation, multiply by x, integrating d3x, integrating d3p, and you get out the equation of motion of your particles in the sense of updating the position as a function of time for that specific f. And similarly, if you multiply by p, Vlasov, integrating d3p, and then integrating d3x, you get the Lorentz force over the particles. Whereas you've seen, I am now using a notation for the electric fields and the magnetic fields that actually does care about the particle that we are considering. And that's because EI is the electric field interpolated at the particle location, which is defined, as you follow the procedure that I described, as the electric field at any position in space convolved with the particle shape. And similarly for the magnetic field that appears in this equation. Okay, so effectively the particle footprint is telling you as well how far you should look in order to know which electric fields are playing a role in the motion of the particle.
I don't know, I didn't understand, but like, why not just start? Because this is kind of the equation for one particle. I mean, it's nice that you arrived to it, but couldn't you have just started with it?
Yeah, but then you don't know what to use for this, right? That's the key. So you can write Lorentz force, okay? We have been writing this since kindergarten. At least I have. I mean, you have not? But to know exactly which value of the electric field you should be considering, that's intrinsically related to which footprint you give for your particles. You could say, oh, I want to use the the closest grid point. Remember, you have fields information only at grid points, right? So I just want to use the closest grid point. That corresponds to a specific choice for your footprint of your particles. Or you want to have some average of the two closest grid points. That corresponds to another choice for the shape function of your particles. So this is explicitly saying how a given choice for the distribution function with the particle footprint is informing the electric fields and the magnetic fields interpolated at the particle location that you should be using to advance the particle equation of motion. I don't know if you want to add something, Sasha. Okay. Good. This is so smooth. You should try the blackbirds at Columbia. It's like, okay, so we went over this already. This is just one slide on particle, actually two slides on particle shapes. Coming back to a question that was asked before, why do you need to choose a shape for the particle? The Coulomb force goes like 1 over r squared, and remember, in these plasmas, we should not capture effects of Coulomb forces on small scales, because we are assuming that the plasma is actually being screened on length scales that are of the order of the Debye length, or larger. So the particle shape is actually coming to our help here. This is a figure taken from La Penta review. Effectively, this is acting, the fact that the particle has a finite footprint is acting as a smoothing length for your Coulomb force. So this is the effective potential of the interaction of two particles with finite size, if the size is half of the Debye length or equal to the Debye length. And you see that the potential never goes to infinity. So you're effectively relaxing or suppressing the effects of binary Coulomb collisions, or the most serious effects of binary Coulomb collisions, by choosing particles of finite size. That's also where this is a convenient choice. Okay, so we're ready to go into the basic particle in cell loop. So this is shown here. As we said, particles are moving in a Lagrangian way in a Eulerian grid. The fields and the currents are known at grid points. And you have these 4 stages. You move particles under the Lorentz force, you deposit the currents. We'll go through all of these stages. You solve for the electromagnetic fields. And then the stage that we just discussed, you interpolate back the electromagnetic fields from the grid to the particle location using the shape of the particle that we just described. And you have many options for the shape. This is a series of properties of the shape, which I've already described. Isotropic, 0 outside some range. This is equivalent to compact support. Higher order, beat splines, this is a specific choice. In general, you can choose something very rough, like a square shape, or triangular, or getting more and more fancy with smoother and smoother shapes. You pay the price of a higher computational cost. You become more accurate, and you're effectively smoothing your binary interactions more and more the higher the particle shape that you choose. I would say most, there are third order shapes that are implemented in the state-of-the-art codes. There are some evidence that at least in 1D and for a specific code, fifth order shape makes a large difference, but I would say this is not the case in which you just say, oh, I'm going to go to 10th order and it's going to be so much better. Not really. Good. I want to add one thing actually before moving on, and then we will be just on slides. So the 2 equations that the PIC method is solving as regard to the Maxwell part are actually only 2. And you might ask, why only 2? And which ones? So together with what I just erased, the other 2 equations that we're solving, in addition to the equation of motion on the individual particles, are the 2 evolutionary Maxwell's equations. So dE dt is C curl B minus 4 pi j, and dB dt is minus C curl E. So what happened to the other 2? What happened to div B equals 0, and what happened to the Poisson's equations, rho E? Okay, just to distinguish from the mass density that you've seen in the hydro course. Why can we get around with this? Why can we avoid solving these 2 equations? In some cases, okay, so we need to be smart in order to be able to do that. So we will see later on, Sasha is going to explain why the specific choice of the mesh, the specific choice of putting electric and magnetic fields on a grid, is automatically guaranteeing that the divergence of B is 0. This one requires a little bit more. I'm just going to sketch a couple of points regarding this one, but you can just trace things in the same way and just work out the same analysis for this one. So you just take the divergence of the first equation. So, and you switch time derivatives and spatial derivatives. This is the Italian way of doing math. Okay, this is 0. And then you have minus 4 pi divergence of j. Now you have another equation for the divergence of j, which is just the equation of charge conservation. Okay, so charge conservation. So if this is satisfied, and that's a requirement for the numerical scheme to satisfy it to machine precision, then if you plug in that one, you get d of dt after a little bit of rearrangement of divergence of E minus 4 pi rho E equal to 0. This is actually a point that Luis also touched on a couple of days ago. So if your algorithm is charge conserving, then Poisson's equation, if satisfied at time equals 0, will be satisfied at all times. Okay? Why is this convenient? Because Poisson's equation is a pain. It's an elliptic equation. It requires knowing information about every grid point. And so it's slow to gather the information about all of the grid points to solve for the electric field at one grid point. The choice of a charge-conserving algorithm then will make your life much easier because you don't need to solve for Poisson's equations. It's automatically satisfied if you are setting up your initial conditions in a reasonably smart way, meaning to satisfy Poisson's equation. And then the only two equations that you have to solve are these ones. And these only need to know information locally. So for advancing the electric field in a given position in space, you need to know the magnetic field, the curl of the magnetic field, and the current at that position in space. So the problem becomes embarrassingly local. Okay? You don't need to reach out to the largest, to the furthest away grid point to know about the information at your grid point. That makes the scheme very appealing and also very easy to extend to high number of cores. So very much parallelizable and scaling very well with number of cores. Everything is local. If you have an algorithm for a charge conserving algorithm. If this is not satisfied, if you don't have a charge conserving algorithm, then you have other ways. You can, so alternatives. Is you solve for Poisson's equations and you correct the electric field if the scheme was not giving you the right electric field that Poisson's equations would like to have, or you use some divergence cleaning. This is similar to what Luis has discussed, in which you're forcing some constraints by solving another hyperbolic equation that will force back the constraints. Okay, but for what I'm going to talk about later, this is the choice. We have a charge-conserving algorithm, and so we get away with not solving Poisson's equation. I'll leave it up for 20 more seconds. Okay, now we'll go into the basic peak loop and then discuss a few applications. So field interpolation we have already discussed. This is the step that you need to do to move from the information at the grid points where you have information about the electric and the magnetic fields to the location of the particles. And that's done by accounting for the particle footprint. In this specific example, the interpolation is a bilinear interpolation, so-called area weighting scheme. Essentially, you're computing how much area you have for in between the particle and the different grid points that might contribute to the information of the electric fields and the magnetic fields at the particle location. This is just one example for one specific choice of the shape factor of the particle. There are higher order schemes that will make your interpolation more accurate but more computationally expensive, as we said. And this is how you push the particles. So how the Lorentz force is implemented, that's not the only way the Lorentz force is implemented, but it's the most popular. And pay attention, because I think this is what you guys will be doing for the practice session this afternoon. Okay, so this is a big deal, because if the number of particles per cell is much larger than unity, most of the computing time will go into pushing particles. So having an algorithm that is efficient will make and accurate will make a substantial difference. The algorithm that I'm going to be describing is called Boris. It's a leapfrog method, which means that the velocities and the momenta and the positions are time staggered. As described here, you know the position at times n minus 1. Knowing the velocity at times n minus 1/2 allows you to jump the position at time n. And if you know the position at time n, you know the electric and the magnetic fields at time n, and you're using them with the Lorentz force to push the particles from n minus 1/2 in velocity to n plus 1/2. Okay, so what I just described in words is written here. You're advancing the position using the velocity at half-time step. The momentum is defined at half-time steps, and it's advanced by knowing the coordinates, and so the values of the electric fields and the magnetic fields, which care about where the particle is located at time n, at integer time steps. Now, what is the complication that you see in this equation? This one is easy, okay? What's the complication here? No, that's a choice. No, the fact that the momentum and the coordinates are staggered in time, it's not a big deal. Okay, what should worry you is the fact that we're trying to solve for this one, right? And this term is also present here. So this is apparently implicit. You need to know this in order to derive it. In reality, since it's linear, things are much easier, and you call this method semi-implicit because you can effectively rewrite it, just making it explicit. So finding the n plus 1/2 as a function of something that is completely known. So this is what the Boris method does, more precisely. This is what you will be implementing. It's doing 2 steps at the beginning and at the end that involve the electric field, and 1 step in the middle that involves the magnetic field. So you say that you do a first half of electric acceleration. So you push the momentum, depending on the electric field, by half a time step. And at the very end, you're taking this sort of like auxiliary variable, you're pushing it again by half a time step according to the electric field. And the intermediate step is connecting this auxiliary P minus with the auxiliary P plus. These two are related by a magnetic rotation, okay, which is described here. The difference in P plus and P minus is just a rotation with some velocity around the magnetic field. And let me stress a couple of things. The magnetic field does no work, right? So we want this step to be conserving the particle energy. It's guaranteed by just doing a rotation. This is not going to change the magnitude of the velocity vector or the momentum vector. And also this implies that once we write here the Lorentz factor of the particle, there is no ambiguity, because you don't need to think about, oh, is this the Lorentz factor before I rotate or after I rotate? Because during the rotation, the particle energy is not changed. So there is no ambiguity about what this Lorentz factor should be. This is equally computed with P plus or P minus equivalently. The Boris method is actually very robust. Even if you are not resolving, for example, the gyro period of a particle in magnetic fields, it's ensuring that your particle is always sitting on the Larmor circle. The phase will be horrible and horribly sampled, but it will still be sitting on the same Larmor circle. And you will see this afternoon. Okay, and then this is basically the whole implementation that connects P minus and P plus to the other variables. So this is what you will be using for the homework or the practice session this afternoon. but it's nothing more than what I just said. So you're pushing the electric field initially, you're pushing the electric field at the end, and you're connecting the two auxiliary variables in the middle by a magnetic rotation that is preserving the particle energy, as it should, because the magnetic field does not work. Okay, and then the charge deposition step, that's another step of the particle in cell loop. This should be symmetric to the field interpolation step to the particle. So the same shape factor that you use to interpolate the fields from the grid to the particle location is the shape factor that you should be using once from the particles you want to deposit the electric currents on the grid. So again, this is an example with the same area weighting scheme. But the important point is that once you choose a shape factor, this shape factor should be the same at the interpolation stage and at the current deposition stage. This is linear. This is bilinear. Triangle effect. Okay, and then the last step to talk about is actually how to solve Maxwell's equations. So the electric fields and the magnetic fields are staggered in time, which means that they are not defined at the same time step, similarly to the x and v for the particles. So the electric field is defined at integer time steps, and the magnetic field and the particle current are defined at half-integer time steps. And the reason for that is obvious, because when you advance the electric field, you want to know the magnetic field at half the step that you're doing. So this is ensuring that the integrator is second order in time, but for both evolutionary Maxwell's equations. And also, the fields are staggered in space, which means that the electric fields and the magnetic fields are not localized in the same position, but they are organized in this way, which is called E-mesh. The magnetic fields are localized at cell surfaces at the center, and the electric field is at cell edges. The advantage of this is twofold. The algorithm is second order accurate in space, once again, because you are staggering the magnetic field with respect to the electric field, and the E-mesh is automatically ensuring that divergence of B is 0. So that also preserves the div B equals 0 constraint automatically from just the choice of putting the electromagnetic fields on your grid. Okay, and I will just be very quick on this. So the only other point that I want to make as regards to the Maxwell part of solving the equations is the fact that the numerical dispersion relation of electromagnetic waves on a grid is not the same as the analytical one. If you have an electromagnetic wave, as written here, the dispersion relation will just be omega equal to c, the speed of light, times k. That's it. Since you're solving the equations on a grid, the grid is introducing a different form for the time and space operators. The curl is different than in analytical. And this is introducing numerical dispersion relation that, after a little bit of algebra, looks like this. So this is for a two-dimensional grid, xy plane, the dispersion relation of electromagnetic waves. And this leads to two consequences. One is, for stability, you need to ensure this condition. This is the Courant condition that will set you the value of the CFL number for a particle in cell simulation that puts a constraint on how large a time step you can have depending on your grid spacing. So for example, if you are in 2-dimension, you'll see that there will be a 2 coming out of here if the grid is has the same unit length in x and y. It will be 3 if you're in 3 dimensions. Large time steps are allowed in fully implicit codes. What I've described is an explicit PIC code. But of course, if you have a time step that is too large, then you're throwing into the garbage a lot of physics that you might actually be interested in. So you might not want to have a time step that large, even though by stability you actually can. But that's a choice related to the physics. And still, as regard to the physics, if we want to capture plasma processes, then we should have a timescale that is capable of capturing the oscillation frequency, the inverse oscillation frequency of the electrons, and maybe the Debye length if you're very restrictive, if not the skin depth, or at least the relevant scales over which plasma physical processes do happen. Maybe I should skip this one, and are you going to talk about it? Okay, so let me skip this one. Boundary conditions, essentially you can do whatever you want. I'm just going to describe here for the fields and for the particles, you can have periodic boundaries. What comes from one side out goes in from the other side. Conducting, which means that you're setting the electric fields tangential to the surface to 0. And absorbing, you're effectively implementing an extra term in Maxwell's equations, this lambda, which is quenching the fields back to some prescribed value, in this case called B in, and the electric fields I want it to be quenched to 0. There are more refined versions of this. They're called perfectly matched layers in multi-dimensions. But these are sort of like further details regarding the scheme. And for the particles, you can have periodic, what comes out comes in, reflecting. This is typically associated with the conducting boundaries for the electromagnetic fields, and inflow-outflow, particles may leave or particles might be injected on the other side. And this is as much as I wanted to say for the core of the particle in cell method. So this might be a good time to pause and see if you guys have residual questions. Thank you for asking the questions, actually. Why do I have to use it? I would say it's a matter of taste. So I am not a big fan of implicit schemes. I'm not using them, actually, other than the semi-implicit Boris algorithm, which is by nature, you cannot do anything but semi-implicit. The main advantage is that you really have no restriction on the time step. So there are a couple of more things. So you have no restriction on the time step. You have generally a better control of numerical heating due to the finite grid instability. Some people claim that it's actually not true, that also the numerical Cherenkov, which is one part that I skipped that Sasha is going to talk about, is solved with implicit schemes, but that's not true. In general, if you're willing to discard some of the physics that happens at very small scales, and you don't want to be computationally bound to be resolving that physics for the stability of your scheme, then I would say go with the implicit scheme. In practice, I think we still miss, and since this is recorded, I'll be very careful. We still miss a good assessment of which part of the physics is it safe to remove. So let me say, for example, that you're getting a time step that is discarding completely all of the electron physics. You want to do an electron-proton simulation, so you care primarily about the proton dynamics. The proton time and length scales are much larger than the electron ones. So you would say, I decide to discard all of the electron scales. Okay? I don't need them because I only want the proton scales. But how much control you have on this subgrid, or not subgrid, but on this physics that you have discarded, I think is not clear yet. For example, do you still have electrons that would have the same temperature as they would if you are actually fully resolving their physics or not? Are you keeping any physics of the electrons? I think this is not settled. Okay. In the same spirit, there are a variety of other numerical approaches if you're interested in scales that are much larger than the electron scales. For example, if you're only caring about the physics of the ions, there is a numerical approach that is called hybrid scheme, which effectively is treating the ions as kinetic particles in exactly the same way that we have discussed here, but it's treating the electrons as a massless charge neutralizing fluid. So it's a little bit in between the particle in cell approach and the fluid approaches. The electrons are a fluid, the protons are kinetic. This is beautifully recovering the proton physics. It's completely agnostic about the electron physics or the electron kinetic physics. And you need, for example, to decide about the electron equation of state, the same way that you would do for a fluid. Um, okay, so this is just to give a broader perspective in the case that you're not just kinetic for every species. For what? So the distribution function, remember, is just like a sum of collection of particles. Okay, so there is no average there. The only average is the fact that we are not really considering the particle as point-like, but it has some shape. So it has some like thickness. The average necessarily go into taking moments of the distribution function to compute the currents. And that's where the shape function comes in. But there is no, at none of these points, or at least in what I've described, there is no time average. You're not carrying information on the current, for example. You might say the current at this time I'm taking from the average of what it is now and what it was the time before. You could, it's probably not a good idea because it's very easy at that point to break the charge conservation that you require for your code to discard the Poisson's equations. It's something that you can not solve. Can you expand a little bit more? I'm not sure I'm getting the question. Um, mm-hmm. So okay, let me try to answer. The time step controls as well what kind of physics you want to resolve. Okay, so you can have a choice of saying, I want to capture physics that happens. Let's talk about time scale and length scale as equivalent. Okay, you want to capture physics that is on the Debye length. Or I don't care about the Debye length, I want to capture physics on the plasma skin depth. Okay, these two are both equivalent choices. Okay, if you need to be aware that if you're discarding physics on the Debye length, then you cannot recover any of the processes that require like Debye length physics, like two-stream instability if it grows on a given growth rate or anything. But that's different than the stability of your numerical scheme. Okay, so it's a question of like which physics you want to resolve. Now, for fluctuations, the fluctuations are also controlled. Let's say you have a given amount and given power in not controlled electromagnetic fluctuations, but those are primarily coming out of particle noise. Each individual particle is a charge moving through a grid. It will provide a microcurrent. This microcurrent will excite electric and magnetic fields by one single particle. The way to suppress this particle scale fluctuations is to have a better representation of the particle distribution function by having more particles per cell, by sampling the distribution with more particles. This allows you to reconstruct the current in a better way, and the current is what feeds into the Maxwell's equation. So if the current is better reconstructed by having more particles per cell, then you're ensuring that your Maxwell's equations do not carry much power into those high frequency or small scale fluctuations. Yes, Pascal.
A couple of numerical questions. Does the techniques you describe are very similar to what they use for particle-laden flows in geophysical fluids?
For particle?
Particle-laden flows, so flows with particles in it. So the question I have, the first one is, for state-of-the-art simulations, how many particles do you typically follow?
I would say few hundred billion.
And then how do you deal with load balancing? Where are you
That depends entirely on the problem. The particles is where the load balancing comes in. So the easiest, so like the easiest distribution of the domain is just like a space decomposition. But now we have dynamic load balancing to account for the fact that the particles might be localized in certain regions of space, especially. Let me just mention one thing that is particularly relevant for the load balancing. I discussed this Vlasov equation both in the context of plasmas and in the context of other collisionless systems like stars. Plasmas are actually much nicer because you have charges of opposite signs. So you have forces that, like for gravity, if you have a concentration of mass, then everything will follow in that spot, and then your dynamic load balancing will become extremely essential to capture the fact that you're in a small region of your domain, you have a whole lot of mass and particles that you want to follow. But here, the systems can have density inhomogeneities, and depending, of course, on the specific system, you can have significant density inhomogeneities close to a pulsar versus very far away. You have a huge density difference. But I would say in the simplest setups, you don't have to worry about strong concentrations of charges. But I'll be curious about the first point that you mentioned, because I'm actually not aware of that. I think it's interesting to see, because the unique thing here is that the particles are not just tracers. The particles are actually responsible for the electromagnetic fields. So if that's the case as well for the fluid perspective that you mentioned.
particle concentrations and train the fluid, and so that drives the fluid motion.
Okay,
It's not
okay.
the difficulty is that in that case you have to additionally solve the Navier-Stokes equation, whereas in your case you don't solve for the evolution of the magnetic field, you just recompute it at every step, which makes it a little bit easier.
It is evolved. It is evolved. The magnetic field is evolved.
In a fairly simple way, rather than the full Navier-Stokes, which is
The momentum is actually much simpler. The particle momentum equation is much simpler. You're just advancing every particle knowing about the local conditions. So that's definitely much simpler. Okay, so I just want to, yep, Drew.
But you're for each particle in your simulation, you're clumping a bunch of its
Effectively.
So why? So when does that break down, and why is that okay?
So it is okay because, as we said, the Lorentz force only cares about the charge to mass ratio. So the charge to mass ratio of that cloud of particles is still the same as for an individual particles. It will break down once collision or collision-like effects become important. The Coulomb interaction of these two macro particles will be very different than the Coulomb interaction of two actual electrons because the charge is different. The charge of this macro particle is much more than the charge of an individual electron. So if you're allowing for interactions, binary interactions of these two macro particles, you're not capturing the right physics for the binary interactions of two electrons. But if you're looking at collective effects in which the particles are interacting with each other only through the electromagnetic fields that they provide through their currents, then it's okay.
And does that have to relate with like the diviron that you were saying?
That has to relate with how many. I mean, ultimately for this systems, we rely on the collisionless assumption. So on having many particles per debye cube.
Would the whole method make no sense to do it with a stellar dynamics or something because you don't have the shielding?
Well, it depends what whole method is. A lot of the techniques that I described here actually do carry over in n-body simulations. I mean, you have leapfrog integrators there for the particles. You do have to solve for Poisson's equations at that point, right? Because that's really the equivalent of what it is here. So then you get into issues of the fact that it's an elliptic equation. You need to know about the conditions everywhere else. But in terms of the integrator, it's actually the same exact concept.
The idea of like macroparticles and superparticles.
It is exactly the same, actually. SPH is macroparticles. It's no different, right? If you're saying I have a star, this star is like 10 to the 4 solar masses. So it's exactly the same concept. No, that's right. That's right. And in fact, in that case, you do have, so that's exactly a good point. In that case, you do have to worry about the fact that you still want to capture binary effects, and yet the binary effects are not properly reproduced. Okay, so I'll just flash through. What do we do with this? We study three things, mostly: shocks, reconnection, and turbulence. I just want to give like a few highlights. Shocks are relevant for gamma ray bursts, stellar explosions, very relativistic, weakly magnetized. The magnetic field in the medium ahead of the shock is much smaller than the shock energy. It's best to phrase this as a ratio of energies in magnetic field versus the kinetic energy of the flow. Are such shocks interesting? They are mediated by an instability that is a plasma instability called Weibull instability. The beautiful thing about this instability is that it's taking energy from counter-streaming flows and putting it into magnetic fields. So we start from a system that has zero magnetic field on the large scales, only microscopic noise level magnetic fields, and the plasma can take the energy of the streaming motions in a shock. A shock is basically like a collision of two fluids, and use it for producing magnetic fields. So we believe that this is why it's magnetizing very relativistic outflows, like in the case of the recent binary neutron star merger event. This is a 2D simulation. This is the equivalent in 3 dimensions. You see this filamentation is a signature of the instability, of the Weibull instability. And I'm just going to flash through, okay, because we're a little bit short of time. If you have questions on anything specific, like talk to me afterwards. Shocks are capable of accelerating particles. In addition to a Maxwellian or thermal-like distribution, you have these high-energy particles pushing in times to higher and higher energies. You cannot have them from a fluid perspective. If you were to simulate this with a MHD code, you have no information about your particle distribution. You're assuming a temperature. That's the only thing that you know about your fluid. But here you can say, I can describe it with a temperature for most of the particles, and then some of the particles are lucky enough to be pushed to higher energies. And the way this is done is through a process that is called Fermi process. It's a process by which particles are bouncing back and forth across the shock. The shock has a converging flow between the medium ahead and the medium behind the shock. So if you're trapped between the two sides of the shock, you're seeing every time crossing over the medium moving towards you. And it's going to push you back with a higher velocity, higher energy. So you're trapped in between two approaching tracks that are, and you're colliding with them at all times. Not recommended. So if you do that, this is one of the particles that we have in the simulations. You see that the particle scatters back and forth. This is the energy as a function of time. There will be especially one time where things are very clear. The shock is located at 0 here. The particle will be advected on the post-shock side. And now when it comes back, you'll see that it corresponds to the kick up in energy as the collision happens. So that's where the particle got the track. And I will skip this and get to magnetic reconnection. So this is another process whose ultimate physics can only be captured kinetically, not in magnetohydrodynamics, for example. It's a process of dissipation of magnetic fields and conversion of the energy of the magnetic field into plasma energy. It's been around for a while. This quote is from Russell Kulsrud, one of the I think most eminent plasma astrophysicists. He got reconnection to study for his PhD thesis 70 years ago, so we still have work to do. And the basic idea of reconnection is that you have magnetic field lines of opposite polarity, pointing to the right here, to the left here. When they meet at the center, the configuration is unstable. You tend to cut the magnetic field lines and reconnect the magnetic field lines, half blue and half red. And this rearrangement of the magnetic field geometry is observed in a variety of systems in the lab, near the Earth magnetosphere, and for more exotic astrophysical objects as well, like the Crab Nebula or jets from active galactic nuclei from supermassive black holes. And especially in that regime, the magnetic energy can be dominant over the rest mass energy of the particle. This regime is called relativistic because if you were to transfer the energy from the magnetic field to the particles will become relativistic particles. That's why this is called relativistic reconnection. And reconnection can actually tackle a number of properties of AGN jets. They require very extended particle distributions with a power law shape. Number of particles differential in energy goes like energy to the minus p. P is the so-called power law slope of the distribution. So as we said, in addition to the Maxwellian, you have a high energy tail of accelerated particles, which could be modeled as a power law. And also, these objects, the supermassive black holes, are observed to vary on very short time scales, as short as 10 minutes. 10 minutes is what we have left. And 10 minutes is also 1/50th of the light crossing time across the black hole horizon for these systems. So we are in the presence of timescale variability that is a factor of 50 smaller than the light crossing time of the black hole horizon, which you might think as the smallest timescale in the problem. So why reconnection can explain that? I'll tell you a little bit of what reconnection looks like. I'm sure Amitava tomorrow will talk more about that. So we start from this configuration of alternating magnetic fields, and we just let it evolve. And all of the subsequent evolution is driven by the self-consistent evolution of Maxwell and Vlasov equation with the particle in cell method. And you see that the reconnection region fragments into a series of magnetic islands. We call them plasmoids. They grow to larger and larger scales. At the same time, you have a constant production of smaller scale structures. So a variety of length scales, a variety of structures. The simulation is much bigger than this, so don't get worried about boundary conditions. This is in 2D, the same thing. Okay, my computer has decided to take a break. The same thing is observed in 3D. So this is the equivalent in 3 dimensions. You see again the formation of these big islands, plasmoids that are merging, and small scale structures are constantly produced as well at all times. So the 2D dynamics, we find it's quite similar to the 3D dynamics, which is reassuring. And in both cases, you have a very broad distribution. So remember, we are obsessed by having high energy particles in these systems. High energy particles require large dynamic range of energies, power law distribution, and reconnection can naturally give power law distributions in the particle energies. This is the equivalent of what I showed before, a movie of a particle on top of the density profile in a reconnection region, and this is the energy of the particle as a function of time. So you'll see the particle getting energized in 2 stages. At the first interaction with this region that we call the reconnection layer, and then nothing happens for a while. The particle is sitting passively in this big magnetic island until the 2 islands collide. The particle is trapped in between, and the particle energy goes up in the second stage. So the first stage we attribute to direct acceleration by an electric field. In reconnection, there is an electric field pointing out of the page in this setup. We call this reconnection electric field. This is what accelerates the particles here. It's direct acceleration. You place the particle in a region with very small magnetic field, very large electric field, the particle will just shoot like crazy. And the second stage instead is the Fermi process that I described before in a different context, but it's still the convergence of 2 flows, and the particle trapped in between is squeezed in between the 2 flows, and its energy goes up. Let me just emphasize one application for jets from active galactic nuclei related to that 10-minute variability time scale that I mentioned before. So we envision that the magnetic islands or the plasmoids that are generated in the layer, if they are shooting towards the observer, might be giving timescales that are as short as 10 minutes. And indeed, this is what we see. So the attention should be now on these small-scale structures, the plasmoids that are moving along the layer, and in some cases they can get to ultra-relativistic velocities. So if you have a blob of particles that is moving relativistically towards you, you will have all of the emission, or most of the emission, Doppler boosted as a result of relativistic effects. And this is responsible for why this is seen as flares in the blazars, because the emission is just increased due to the motion of these structures towards the observer. Get to the next one. Okay, so this is ultimately what we can do. We take our particle in cell simulations of reconnection. Every one of these structures will be able to give radiation, emitted light. And what I'm showing here is the resulting spectrum. This is powered by synchrotron emission. This is powered by inverse Compton emission, and the gamma ray light curve. So every spike here, and you'll see it as the movie progresses, is given by one of these plasmoids, one of these magnetic islands that are shooting towards the observer. So the time variability is imprinted by the self-consistent dynamics of the reconnection layer. That large guy was responsible for the overall rise of the light curve at later times, as you will see it again. So this overall rise is powered by this very large plasmoid moving towards the observer. And this is consistent with the 10 minutes. So for the fastest flares, we get down to 10-minute variability timescales as we need for these systems. And the last piece that I want to describe is how can we use these simulations to give better inputs to models, GRMHD, general relativistic magnetohydrodynamics model of the emission from black hole disks, or low luminosity accretion disks, which, as I said at the beginning, are collisionless. And the collisionless assumption is, or the collisionless nature of the accretion disk has two consequences. First, nothing prevents the electrons and the protons to have different temperatures. If they're not collisionally coupled, they can just stay at different temperatures. And two, you can have in principle non-thermal electrons accelerated at higher energies that are not sharing their energy with the bulk of the plasma, and they can still keep their higher energies. So that's basically what we can do. We can postulate that reconnection is the ultimate source of dissipation in this system. So the energy of the system, which is in flows, in like rotation, in turbulent motions, ultimately is processed by reconnection. That's an ansatz. It doesn't need to be the case, but it's a, I think, well-motivated ansatz. And then we can say how much reconnection is capable, for example, of partitioning that energy into electrons versus protons. So in applications for that, we have also performed a few simulations of turbulence with the idea of trying to understand whether magnetic reconnection with this presence of current sheets can be at the base of an ultimate turbulent cascade. So in turbulence, the energy comes from large scales and eventually goes down to very small scales. And there's been a series of works in recent years that said that at the smallest scales, you actually have reconnection. So the ultimate dissipation of turbulence for a variety of systems happens through reconnection. So this is a snapshot from one 2D simulation of turbulence that we have performed with particle in cell. It's a zoom in on two different structures. You see how fragmented it is, and in some cases you see the same plasmoids that the earlier results of reconnections were showing. So you do have reconnection as part naturally of a turbulent cascade. And that's okay. I will close with this. This is a scan through a one snapshot of a 3D simulation. So you will see it as a movie, but it's not time evolution. It's just different slices through a 3D simulation of turbulence. And what's lighting up here are primarily reconnection layers where the particles are energized first. So the first episode of particle energization happens at reconnection layers. They're very important for the turbulent cascade. And I will stop here exactly at 0, but it stayed 0 for about 1 minute. So Okay, thank you very much.
So you have turbulence, and you have, but this is like collisionless. So you have no dissipation.
So ultimately, there is no dissipation in the sense of the energy stays in the system. Okay, so it's not like when you have in MHD turbulence that you have, um, you can say isothermal equation of states. And in that case, your turbulence is happening at all times. You can drive the turbulence. The system is not heating up. Um, the dissipation is happening. It's putting energy into particles' heat. The way this is done is not numerical. That's really the beauty of this, right? That if any physical process that will give you dissipation is dissipation ultimately caused by plasma physical effects. Landau damping, okay? That's a process that takes the energy of electric fluctuations and it's putting it into particles, okay? So that's one dissipation, you can call it. It's dissipation of some form of energy into another form, into heat. But it's something that the kinetic physics of plasmas can capture reliably. You have no uncertainty in, am I prescribing the correct rate for the dissipation? Here, the dissipation is provided by collisionless effects. Okay, so you have no collision provided a dissipation, but it's provided by collisionless effects, which are effectively acting as a dissipation process. The same is true for reconnection, actually. Reconnection, you might say, needs resistivity, right? Resistivity is a collisional process. What are we talking about? Now, that's where the concept of anomalous resistivity comes in. You can effectively have a plasma in which plasma wave effects are effectively producing an effective collision frequency. Think about it this way. Collision is a particle wants to move in a straight line and something else diverts it from that straight line. Now, that something else can be the head-on billiard ball collision with another particle, but it could be interaction with large-scale electric and magnetic fields produced by the collective effects of the particles. So effectively, this is still kind of collisions, even though it's not induced by binary processes.
So the kinetic energy goes to some other kind of, is transferred to some other energy.
The kinetic energy and the magnetic energy of the turbulence goes into heat, ultimately. The plasma comes out hotter. It comes out also with a non-thermal distribution of particles, so it's not just thermal heat, but also some particles are accelerated, which is interesting. But ultimately, this is where the sink is. The sink is heat.
And sorry, but does it feed back then this heat into the kinetic energy as well? Like, is it,
Absolutely, yeah, absolutely.
can you say just a little bit?
It depends on how you set up the system at that point. So this simulation is a simulation of decaying turbulence. So we start from a configuration that is leading to the development of the turbulent cascade, but we don't constantly drive it. So whatever is left at the end, there is no more kinetic energy in the bulk of the turbulence. There is no bulk kinetic energy of the turbulence. There is very little magnetic energy of the turbulence left at the end. So even, I mean, there is an effect, but the effect is minor because the turbulence has disappeared. Kai has been performing driven simulations of turbulence in which you constantly drive turbulence, but you cannot get rid of the heat. So the heat is effectively changing the properties of the turbulent cascade the longer you drive the turbulence for. You guys choose, I don't know. Benjamin first. So that's not a work that we have done yet. What we have done is to look at places where the injection happens for the high energy particles. So the question that was driving was not what is the nature of the dissipation in turbulence, but more for selecting a few particles out of the thermal pool and promoting them to high energies, what is the role of the reconnection layers? And they are extremely important. We find that like a large majority of particles that eventually get to high energy need to go through the reconnection current layer. I mean, the effect of, I would say, for this, It's possible. I just don't know yet. Yeah, I mean, the
You should remember that this is relativistic.
yeah, exactly, exactly.
Reconnection is much more efficient than anything else once the energy is stored in the magnetic field initially.
Yeah, that's a very good way of phrasing it. Like it's always a question of where most of the free energy is. The same way that in shocks I've not mentioned reconnection is because most of the energy is in the bulk kinetic of the flow. This turbulence is relativistic, meaning strongly magnetized turbulence. So the reservoir of energy at the beginning is mostly in the magnetic field, and then it is the dissipation of the magnetic field that ultimately leads to interesting heating and non-thermal signatures. Now, what happens in the reconnection regions and whether the effective resistivity that you have there can be described in which way, and whether you have some kind of like two-stream instabilities there that are effectively providing your collisions and your resistivity, it's possible, but I don't know the answer.
So how can you, if you don't have explicit collisions, with regards to thermal heating and the H theorem, how can you be sure that you're doing your thermal heating right if you're not actually?
It's an excellent question. Yeah, I guess it depends ultimately what you want to measure. The system is collisionless. It should not produce entropy. Okay, so entropy should be conserved. How you're measuring entropy? If you're measuring entropy in a coarse-grained way, then entropy can actually increase. Okay, if at some point this becomes too complicated, we'll just stop. Okay, but you can say, for example, the same thing happens in collisionless stellar systems. Okay, they should be entropy conserving. You can coarse grain entropy, saying I looked at given chunks of the phase space and I'm computing my entropy as the integral of f log f, binned with those chunks in phase space. And you'll see the entropy increasing. But it's just of a result of the fact that you're coarse graining your distribution function, which is also inevitably what we do here. So I think it really is a question that comes down to what you're measuring. Okay, if you're interested in thermal heat partition, it's a well-posed question. You can always say, I want to decide, I want to see how much of the energy goes in one species versus the other. You can check your numerics for convergence against that answer by going more and more into a regime in which the binary Coulomb collisions between your macroparticles should be inhibited. And if your answer is the same, then you're sure that even in the extreme limit in which every particle, every macroparticle is an actual electron, then the same thing will be true. But at the moment of talking about entropy generation irreversible processes, then you need to be very careful in saying I'm actually taking a coarse-grained description and I'm quantifying this from the coarse-grained point of view. Now, the way I like to think about it, we might become a little bit technical here, is even within this coarse-grained description, effectively what you're saying is I cannot really capture sort of like small scales in my distribution function that are below the bin size of my entropy calculation. Okay, so if your actual distribution function analytical is like this, okay, and then it's like I cannot intersect, but it's a okay, and imagine that you go swirl and more and more and more, okay, and your bins for the entropy are like this. Then you're effectively taking this and say I just have like one value for the temperature of the distribution function in that bin. Does it make sense? Not really, because in reality, your distribution function is just like very, very convoluted. Now, it is also conceivable that for any system, very fine structures of your distribution function in physical space and velocity space. So if you're going to the high K regime for the physical space and the equivalent high K regime for the velocity space, a minute amount of collisions will actually get rid of those gradients because they're happening on such a high K scales. And at that point, you can say, oh, I'm envisioning that the overall dissipation is still controlled by large scales, much larger than this, because this is determining eventually how the distribution function is going to roll over and tangle. But then the fact that that tangling, which is in principle infinitely thin and infinitely tangled in a collisionless way, is erased as a result of as small collision rate as possible, will not affect the dissipation rate, because the dissipation rate will still be controlled by how much the large scales are pumping into that state. Okay? So I don't know if this confused you more or clarified things more, but the equations are collisionless, the entropy should be conserved, the coarse-grained entropy not necessarily. At which level the coarse-grained entropy increase is giving you an actual assessment of the entropy generation that you would be having if you were to have an even small amount of collisions. I would say quite likely.
Pessimistic comment here could be that if you want to model that, you need other methods.
That's true. Yeah, absolutely. So inevitably, the peak description being, I would say, finite in either particle shape or in spatial resolution will sooner or later run into issues of not being able to capture the properties of the distribution function at such high k, or I k in velocity space. Okay. Coffee time. Thank you for the questions. It was great.